In our initial film, we explored the numerous apparent contradictions throughout world history that remain scientifically unexplained. The widely accepted chronology, devised and largely finalized by historians and philosophers like Joseph Scaliger and Dionysius Exiguus in the 16th and 17th centuries, dates human history from ancient times to the present day. This chronological framework is meticulously organized in historical and archaeological texts, as well as museum displays, showcasing artifacts from various eras. However, questions arise regarding the reliability of dating methods used to assign specific ages to these artifacts. While it's commonly believed that these methods are rigorously tested and highly dependable, our film aims to scrutinize this assumption and question whether world history is truly founded on irrefutable scientific evidence. The excavation process serves as the starting point for this inquiry. Archaeologists delve into ancient settlements, where layers of human activity over centuries have accumulated. Through stratigraphy, archaeologists discern the sequence of these cultural layers, each potentially containing artifacts that can be dated using various scientific techniques. Yet, dating by analogy, a common method, relies on similarities between artifacts rather than precise scientific measures, leading to potential inaccuracies. For instance, a ring discovered in Novgorod may be dated to the 12th century based on similarities with another ring found elsewhere, highlighting the limitations of analogical dating methods. Indeed, relying solely on similarities between artifacts for dating purposes is a rather crude method. While it may suggest that items are from approximately the same period, it overlooks significant nuances. There's a chance that two items appearing similar may have been produced at different times. This subjectivity becomes apparent when one archaeologist's interpretation of similarity differs from another's. Moreover, culturally significant or cherished objects could be passed down through generations, leading to misconceptions about the age of associated structures. Thus, the dating method by analogy lacks a firm scientific basis and fails to provide even approximate ages for finds. Alternatively, archaeologists often turn to cultural layers or burials for dating, sometimes aided by the discovery of ancient coins. Unlike many modern coins, ancient coins typically lack inscriptions of minting dates. Instead, they might bear images of rulers or symbols, which were not consistently tied to specific time periods. While exceptions exist, such as the unique discovery of Bosporan coins in Crimea, identifying the age of coins based solely on imagery or ruler names can be misleading. Examples demonstrate instances where rulers' images persisted on coins long after their death, or where imitation coins circulated for centuries, complicating accurate dating. Therefore, while coins can offer valuable insights, their use as sole indicators of chronological age is fraught with uncertainties and exceptions. Here's another example. The renowned Greek coin, the tetradrachm featuring Alexander the Great, has become increasingly valuable over time. Minted widely in Athens, this coin circulated along the Black Sea coast, in Asia Minor, North Africa, and the Middle East. Finding such a coin in the cultural layer of an ancient city poses challenges in determining both its age and that of the surrounding layers. Notably, the presence of the emperor's portrait does not necessarily provide clarity. While coins bearing Alexander the Great's likeness were widespread, they weren't solely minted within his empire's borders. Adjacent lands also produced them. Thus, a sovereign's portrait doesn't always indicate the coin's place or time of minting. Moreover, in ancient Russian settlements, archaeologists often uncover silver bars instead of coins. Since these bars lack inscriptions or distinctive features, determining their age relies on approximations based on historical context rather than precise dating methods. Despite these challenges, archaeologists emphasize the importance of coins in establishing relative chronologies. While not foolproof, coins offer valuable insights into past economies and cultures, underscoring their significance in archaeological studies. In both ancient times and today, clay was a readily available material used extensively for crafting homemade utensils like pots and plates, leading to vast quantities of ceramics being the primary material found at archaeological sites. To determine the age of these clay products, scientists have attempted to utilize the archaeomagnetic method. Clay inherently contains minuscule iron particles, making it capable of magnetization. However, upon firing clay at temperatures exceeding 600 degrees Celsius, its magnetic field essentially freezes, retaining the magnitude and direction of the Earth's magnetic field at the time and place of firing. Yet, accurately dating a specific ceramic object, such as a jug, after hundreds or thousands of years is incredibly challenging. It requires understanding not only how the Earth's magnetic field has changed over time but also the specific conditions of the firing process, such as the evenness of heat distribution in the oven. Despite attempts by enthusiasts, the archaeomagnetic method remains unreliable due to the Earth's unstable magnetic field, making precise dating nearly impossible. Similarly, the concept of measuring time through sediment accumulation, akin to the markings on an hourglass, gained global attention but yielded disappointing results upon examination. Sediments accumulate at varying rates depending on factors like sediment type and climate zone, making it unreliable for precise dating. For instance, while a structure buried under sand in Egypt might suggest a certain age, sediment accumulation rates vary greatly across different regions and sediment types. Consequently, relying on sediment accumulation as a dating method has proven unreliable, leading to inaccurate estimations and necessitating reassessment of initial calculations. Thus, this method has fallen out of favor in archaeological practice due to its unreliability and inability to withstand scrutiny when applied to diverse contexts. In conclusion, the method of dendrochronology is primarily applicable to determining the age of modern sedimentary deposits, with limited application to ancient deposits. However, archaeologists consider it a significant success when an archaeological site yields numerous wooden fragments, as dendrochronology enables precise dating of objects to within a year or less. This method, developed in the late 19th and early 20th centuries at the intersection of geography, history, and biology, relies on the annual growth rings of trees. Each year, the width of tree rings varies based on environmental factors like temperature and rainfall. By comparing the tree rings of a found wooden structure to those of reference trees, dendrochronologists can establish the structure's construction date. A dendrochronological reference scale, researchers analyze the annual rings of living and dead trees. However, a limitation arises in European forests, where living trees typically only offer a reference scale up to around 500 years ago. Beyond this, dead wood samples are necessary to extend the scale. Despite efforts by scientists across European countries, gaps in the scale, or voids, emerge beyond the 1000 AD mark, requiring additional data accumulation and research to fill them. This ongoing scientific endeavor highlights the continuous need for advancements in dating methods to accurately date wooden finds, particularly in Europe, where trees cut down after the 1000th year AD offer limited potential for precise dating compared to regions like North America, where trees can live for thousands of years. For instance, a single living sequoia or bald cypress tree can provide a dendrochronological scale spanning back 4,000 years. However, this scale cannot be directly applied to dating wooden finds from Europe and Asia, where civilizations developed independently. These regions host the main historical monuments of humanity, but dendrochronology faces challenges in dating artifacts due to various factors. For example, finding a single log in a burial site is insufficient for accurate dendrochronological analysis. Ideally, several dozen logs are needed, which are not always available in excavations. Therefore, historians sometimes rely on historical considerations rather than dendrochronological results to date artifacts. Moreover, the processing and storage of wood further complicate dendrochronological dating. When wood is processed, its outer layers, containing several rings, are often removed. Determining the outermost ring of a log is crucial for accurate dating. However, if this outermost ring is missing, researchers must estimate its age based on the number of rings present. This estimation can sometimes lead to inaccuracies. For example, assuming a log has 20 rings could result in an estimated age of 1,220, but if it actually has 100 rings, the age could span an entire century. Despite these challenges, dendrochronology has been successfully applied in archaeology, such as in dating the layers of pavements in Veliki Novgorod. By analyzing the tree rings of preserved pine logs within the pavement layers, scientists concluded that the pavement layers were constructed over a period of 550 years, dating back to the 15th century. However, questions remain about why earlier pavement layers, particularly those predating the 15th century, have not been similarly preserved. These discrepancies highlight the limitations of dendrochronology in providing precise dating for archaeological monuments, as it relies on specific criteria that many sites do not meet simultaneously. Today, radiocarbon dating analysis stands as the primary method for determining the age of archaeological finds. This physical method is utilized for dating objects and materials of biological origin. Proposed by American physicist Willard Libby in 1947, radiocarbon dating is specifically applicable to organic objects such as animal remains, wood, fabric, and paper. The process involves several steps. Biological organisms contain carbon, including the stable isotopes C12 and C13, as well as the radioactive isotope C14. C14 is continually formed in the atmosphere due to cosmic ray radiation, with an estimated 7 kilograms being produced and disintegrated annually at an altitude of 15 kilometers. This radiocarbon then enters plants through photosynthesis. Animals consume these plants, and humans in turn consume both plants and animals, thereby incorporating radiocarbon into their bodies. Upon the death of an organism, the exchange of carbon ceases, preserving stable carbon in the remains while the radioactive C14 gradually decays. By measuring the remaining amount of radiocarbon in a sample, scientists can determine the time elapsed since the organism's death. This method is applied in laboratories worldwide, as showcased by scientists in Moscow, who carefully prepare and analyze samples, such as an antelope skull fragment from excavations in Ethiopia, to ascertain their ages. The process involves various steps, including the removal of impurities, acid treatment, and the collection and analysis of acetylene gas released during sample combustion. This meticulous procedure allows researchers to derive accurate dates for archaeological specimens, contributing to our understanding of the past. After defrosting in the second trap, the gas passes through a liquid washing and then enters the flask containing activated carbon. The washing liquid purifies the gas from potential impurities and alkali, while the drying agent removes water vapor. Acetylene gradually accumulates in this trap before reaching the hot catalyst, which is removed from the oven and placed in a housing with water at the bottom, where benzene is formed. The final trap is connected, and the catalyst is returned to the oven. Once benzene is collected in this trap, it is carefully introduced into a container and placed into a measuring complex, where a calculating machine determines the radiocarbon age of the sample. The data obtained from the machine is entered into a computer program, converting the radiocarbon age into a calendar date. For instance, an African antelope lived between 790 and 510 BC based on our research results. However, the resulting dating isn't always accurate due to various errors inherent in the complex measuring system and its operation. Factors like changes in the concentration of carbon in the atmosphere, solar activity, and magnetic field strength can affect accuracy. Additionally, the bomb effect caused by nuclear tests in the 1950s has doubled the concentration of radiocarbon in the atmosphere, leading to discrepancies in the ages of certain organisms. Wooden buildings pose particular challenges as radiocarbon dating determines only the period of tree death, not necessarily when it was used for construction. Similarly, dating written sources such as ancient scrolls is complicated by unknown storage histories and treatment methods. Despite using computer programs and purification techniques, errors still occur, with approximately 1 in 10 radiocarbon dates obtained from the best laboratories worldwide being significantly inaccurate. Continuing to utilize radiocarbon dating, hundreds of thousands of dates have been obtained worldwide, constituting one of the most crucial methods, particularly for dating objects up to 40 to 45,000 years old. While this method has its limitations and potential inaccuracies, multiple measurements can ensure more precise dating. In a notable case in 1988, renowned radiocarbon analysis laboratories independently studied fragments of a certain canvas, the Shroud of Turin, via blind testing, where researchers were unaware of the sample's origins. Despite the shroud's legend dating back to Christ's time, radiocarbon dating suggested a much later origin, sparking debates about its authenticity and raising questions about the accuracy of the dating method itself. Such discrepancies highlight the complexities and potential errors inherent in radiocarbon dating, particularly for historical monuments whose ages span thousands of years. Of up to 2,000 years may be acceptable for monuments with longer histories, they are deemed unacceptable for objects dating to 2,000 to 4,000 years. The imperfections of existing dating methods underscore the need for improvement and the accumulation of new materials to enhance accuracy. However, despite these challenges, historians and archaeologists continue to interpret historical events, albeit with recognition of the limitations of current dating techniques.